Hello everyone and welcome back to Science Y. Christmas lights. Now I know yours have probably been down for a couple of months. These ones are just ones that we have up that are solar powered in the back garden. But what's going on in this? And what's inside there? Well, I broke one open so we can have a look. Let's find out what's going on. So lots of Christmas lights have this sort of unit on it, and this is how you turn them on. Alright guys, so slightly a different backdrop today. I've got the little view of the garden out there behind me, and I've just been out in the garden and I've used one of these to smash up one of these and have a look at what's inside of it and the components. Now I spoke last video about these, and so hopefully if you watch that video you know what these are called. And this little component here, which is found just inside there's a few other components, various capacitors maybe, so on, but this is the bit I'm interested in. And this is a very tiny transformer. So although these days we can make the components really tiny, this is what an old transformer would have looked like with the primary and secondary coils. You can see the coils of wire there. We might have used something similar in the lab in the olden days. And if you look at these types of transformer that you will find at the substations and the little residential substations, also still really big. Okay, now the thing that's important about transformers is there's two coils. There's a primary coil and a secondary coil. So a little photo that I took from the Combined Science textbook here, guys. You can see that there's 5 turns on the primary coil, and on the secondary there's 10 turns. That makes this a step up transformer. There's more coils on the secondary coil, more turns on the secondary coil I should say, than on the primary. And full disclosure here guys, I'm going to sneak in a little bit on equations. Because as part of our GCSE, there's something called the transformer equation, our GCSE paper 2, that we need to be able to use. And just like all the equations currently in combined physics will be given to you, you don't need to remember the equation. What you need to be able to do is rearrange it. And here it is in all its glory, guys. The transformer equation, cunningly pictured from the Combined Science textbook, and this is the one I will be using. You don't need to remember it, it will be on the equation sheet on your exam. And as someone, full disclosure, who isn't the best at maths, and I may upset some maths teachers here when I admit that I do like to use formula triangles, sorry, but in this particular case you need to rearrange the equation without the triangle. So you're either rearranging it before you use it, or you put the values in and then you rearrange it as you go. So I will be showing you that as well, which is sort of the main thrust of this really. But going back to our Christmas lights for a moment, just like I said in the previous video, we need the voltage to be reduced. We need the voltage to be stepped down. So when I was younger, guys, in the old days, the Christmas tree lights used to just run off the mains voltage, and that was dangerous and used to cause fires. So what is the point of the step down transformer in the modern lights? Safety. And that's what this thing here does. So this example question, we have a transformer with 33,000 volts. Now, it is worth bearing in mind here that we do need that to be in volts. And if it's not in volts, we need to convert it to volts. And I'll come back to that in a bit. So if it's got 33,000 volts applied to its primary coil and a current of 2 amps in the primary, the secondary coil gives an output of 230 volts, which is mains voltage over here, but how much current is in the secondary coil. So basically it's asking us for this one. So a good thing to do sometimes is just to write down the values, and there's 2 ways to attempt the equation. Either we put the values in and then rearrange, or we rearrange before we put the values in. So let's have a quick look at both ways. So if we do write the values in, we'd need to rewrite the equation quickly. And then we put the values in. So it's important to know what's what. So voltage in the primary is 33,000 volts. Current in the primary is 2 amps. Voltage in the secondary coil we know is 230 volts. And that's the one that we don't know. Now, this is where you divide out. It's as simple as that. So we're dividing out, guys, and we need to do the same to both sides. So we want to leave this on its own, which means we divide that by 230. That cancels, leaving IS on its own. So current in the secondary coil, which means we need to divide this side by 230 as well. And that basically leaves us with the equation that we need to do. So 33,000 times 2 amps divided by 230 is equal to IS. So I've written that in there, guys, and I always go step by step when I'm doing this, just so that you definitely get it right. Show all your working out, because you can still get marks even if you don't get the answer right and make a mistake with your calculation. But 66,000 divided by 230 works out at 286.95. Now, I can't round down to 0.9 if it's one decimal place, so it'd be 287.0 if I was doing one decimal place, but I'm going to leave it as 2 decimal places for now, and that is the answer. And of course, we then need to look at what our units are going to be. The answer, we're looking for the current in the secondary coil, so the units for current are amps, and there's our answer. Okay, so I've had to re-record this because I did it all really nicely and it was completely out of shot when I did it. So the other way of doing it, as I said, is to rearrange the equation first. So remember, we want IS. Alright, so we divide to get rid of VS over here. That cancels, and we always do the same to both sides. So that's VS there. Yeah, so our new equation would be IS is equal to VP times IP divided by VS. Now I did that again, and I got exactly the same answer as I did before. So our answer, if we put it into this equation again, we get the same answer, 286.95 amps in the secondary coil, which is IS. So S for secondary, I for current. But something that you might find interesting is you would have noticed that the current increased from 2 up to 286.95 in the secondary coil, whereas the voltage in the primary has gone from 330,000 down to 230. So what you'll notice is, while the current increases, the voltage decreases. And you may think that that's a mistake. It's not. The current does the opposite of the voltage, okay? Which is why on an overhead power line, we step up our voltage, because that reduces our current. And the reason we want to reduce the current is because current creates heat, and heat creates energy losses from the system. One last quick thing, I mentioned converting units, because this question that I did originally, in the question it had 33 kilovolts, not 33,000 volts. So all I did, just to make the question a bit easier, is I converted it. But that's how they might try to not catch you out, but you can get kilovolts and megavolts and so on. Kilo is 1,000, so 33 kilovolts converts to 33,000 volts. Okay guys, so I'm back out in the garden, and you'll hear a little bit of sound from the neighbours' children playing out as it's half term. So now we know a little bit more about the transformer equation, we can understand a little bit more about how lights like this work. that's it for another video, guys. Hope you've learned a little bit of useful stuff there, and I hope to see you again on Science Y. Right, so this is... come on. And now we know how these lights work, okay? And we also understand a bit about the transformer equation.